So class, today's lecture is largely a video from last time. I'm starting off with some announcements. The latest two homeworks have been posted on the website. You did not need spring break to worry about them. Spring breaks for recharging. They are pretty easy. There's the exploitation homework, and then there's also the Wireshark and packet capture hunting homework. And they are not due at the same time, so don't worry about having three homeworks at once. So the rest of today's lecture is going to be an old video, so I apologize for that, but all the content is still relevant. So we went over basic web architecture components, how users have their web browsers and they interact with the web server, which is usually behind some sort of firewall, but it has a public IP address and it's running a web service like Apache or Tomcat, running a database to handle all sorts of types of content for the web application. That's either Microsoft SQL Server or MySQL or some other variant. And there's tons of different database types other than just SQL. So you have access control mechanisms and then authentication services, and then there's all sorts of attacks out there. And we went over quickly, basically, just like how many attacks there are, but we didn't really go into detail on each one as to what they target. Do they target the users? Do they target the server? And then you have, aside from those attacks on a generic web architecture, you have commonly on architectures, you have things to support dynamic content like Ajax, you have Flash for YouTube videos and anything else like that, Silverlight, perhaps on Netflix, and then Java and things like that, their applets, and so much more. And all these are subject to ODAs that usually are targeted against users. And this makes the art of hosting a web application and browsing a web application one that is, in theory, having a huge attack surface. So a lot of the feedback I've got so far is a lot of you wondered about the big picture and how all the topics we've covered so far really fit together, like reverse engineering, writing shell code, and all these things, and networking, firewalls, NAS, and how this really fits in the big picture. So since we're going over web application hacking, I figure this is the best place to address the big picture, bring everything together, and that basically you want to look at it that you have users and then you have servers. The servers can have all this stuff going on in the background, and they're usually behind a firewall. However, users are usually behind a firewall and a NAT. And the NAT, as we covered, basically creates a private subnetwork that is not directly addressable from outside the network. In other words, an attacker can't just sit outside of your firewall that's properly set, outside of your router that's properly set up and start attacking your system. They have to defeat the firewall somehow first. So NAT is an extremely effective mechanism for preventing users from getting attacked in general. And thus, when users are attacked, it's usually not direct. So when users browse the internet, servers respond perhaps in HTTP with both data and code that can be executed on the client's browser. And typically this sort of code is something like JavaScript, VBScript, HTML5. And so this can create problems whenever you're mixing code with data. So like I said, users are rarely ever attacked directly by hackers or malware, as the NAT prevents most just direct attacks. Instead, users commonly face many indirect attacks in that they are attacked by things that are perhaps hosted on good websites that were just vulnerable, and a hacker broke in and put some malware somewhere. Perhaps it's a cross-site scripting attack that will attack you whenever you visit that page or that content, and perhaps do things like steal your session ID. Servers are constantly directly attacked by hackers. Now that's where the art of writing shellcode, reverse engineering things, finding bugs and vulnerabilities, buffer overflows, metacharacter injection, integer overflows all come in handy in finding vulnerabilities to exploit in web application architecture components. The web service itself is typically something like Apache and handles packets going in and out, and well, rather, since it's an application layer, application packets or data. And so finding vulnerabilities in common web servers nowadays is growing rarer and rarer because those have been around long enough that they're pretty secure. Every now and then you'll find some big vulnerability that comes out, but it's usually handled by the security community. And these other things, vulnerabilities often arise by the application developer's failure to handle special cases when interfacing between components. Most commonly, Metacharacter injection. It's completely overlooked and allows you to pass data, something that looks like data from one component to the next component behind it that interprets it as code. So while we're talking about Metacharacter injection, these things are all commonly attacked, and other ones that aren't listed here. So this slide pretty much covers what I just said so far. And then it brings us to how servers can be subverted to attack users. Dynamic content is everywhere today. Feeds pull content from other websites, from other domains. There's embedded remote resources. Perhaps there's the latest YouTube video posted on your Facebook feed. There's advertisements, perhaps Google advertisements, perhaps advertisements from other services that could perhaps even have JavaScript running in the ad. There's always viral videos. There's features to sign into a website with Twitter, Facebook, or Gmail. And then there's so many more. You know, users are often attacked by malicious content that executes code on their machine. Usually, the malicious content exploits some vulnerability in whatever application is used to render that media, say for YouTube videos. It's the Flash player that's running in your browser. If that has a vulnerability, it's completely theoretically possible for someone to upload a malicious video on YouTube, get people to view it, and then it infects their machine perhaps with malware. Other common other common vectors include client-side scripting, such as JavaScript, ActionScript, and I'm repeating myself at this point. And so, yeah, you have the dynamic content attacks, Flash, the applets, SQLi, and so the content attacks really aim at targeting vulnerabilities in web browsers, vulnerabilities in browser plugins. Perhaps you have a third-party PDF reader plugin in your browser, so you don't have to open up the bloated Adobe Reader every time. So perhaps you have Foxit Reader. And then you have all sorts of vulnerabilities perhaps in these third-party plugins too. Third-party plugins really don't get as much attention as they deserve security-wise. They're often overlooked as a potential vector for defenders to be attacked. And so all those plugins can have buffer overflows, integer overflows, etc. And basically all it takes is for an attacker to upload perhaps a viral video, the latest Harlem Shake, and they get millions of people in one go. And it's pretty much that simple. But it depends on them finding a vulnerability in order to do that the community hasn't found and fixed first. So while we're attacking users, it's important to note that admins are often users on their own websites too. And it's common for attackers, when they're attacking users, to target specifically the admins. These types of attacks are usually focused on stealing session IDs and stealing cookies. So perhaps for a forum admin or the content management system administrator account. So you have things going on like cross-site request forgery, cross-site scripting, dynamic media ODays, and browser ODays. But this is all, we could talk about this all day, but we want to go about this in the formal way. So there's a great website called OWASP. I'm going to go to it right now. It's basically the Wikipedia for open web application security. Anything you want to know about web application security and or hacking can be found pretty much on this website. If you want to find ways to defend against SQL injection, there's wonderful cheat sheets and often videos, tutorial videos on how to defend against them, as well as cheat sheets on how to bypass most common defenses in order to assess the vulnerabilities in your web application. It has wonderful articles on explaining the basics of browser security and web application security, and I highly recommend it for anyone struggling with any of the future homework in this class related to this topic. So every 3 or 4 years, they categorize and rank the top vulnerabilities out there. And they compile this into a report called the OWASP Top 10. And this is commonly referred to in many lectures, talks, and papers. You'll hear it all over the place. And the OWASP Top 10 was, as of today, last updated in 2010. And I have the 2007 version here for comparison. The top vulnerability here is injection flaws, and that covers SQL injection. Cross-site scripting is also an injection flaw, but it deserves its own category because it's very unique and it's distinct. And many of these things do not change over the years. Injection flaws such as SQL injection were introduced over a decade ago, and they're very simple to defend against. However, things like cross-site scripting are very difficult to defend against. They're conceptually very difficult for web application developers to grasp. And thus, there's many instances of vulnerabilities, XSS vulnerabilities in common applications. But you'll see basically the top 5s haven't changed, and really only this, I think, just got renamed. And for the most part, the trends kind of stay the same. SQL injection is still today the #1 way to break into a website and most commonly exploited by attackers. Then cross-site scripting, and then the rest. We're going to go over SQL injection and cross-site scripting today. Hopefully we'll get through all of it. So in the OWASP report, I chose this material because this is really a good way to formally approach vulnerability assessment for web applications. Basically, early in the semester, I think the first lecture, I said that an important equation, rough equation to remember, is that risk equals threat times vulnerability. In other words, your enterprise or your business's risk is a function of all the vulnerabilities you have and the willingness, ease of access, availability, and persistence of your threat vectors to attack those vulnerabilities, among other things. So here in this diagram, you essentially have threat agents, and then for your web server, you should try to identify the common attack vectors, such as SQL injection, cross-site scripting, and identify any pages on your website that those might apply to. Some pages are just static pages, so they won't have any dynamic content interfacing with components like a database, stuff like that. And then for those ones that you identify that are weak, you identify the controls that you have in place to secure against these attacks. And then if those attacks somehow succeed, you identify basically the technical impacts and the business impacts. The impacts can range from being absolutely trivial and doing no harm to completely putting you out of business. I often like to cite the case of HB Gary when they were attacked by Anonymous. It was a long attack chain involving hacking the web application, social engineering, and other stuff. But it all began basically with SQL injection. And from there, they were able to, at some point later in the attack chain, impersonate the CEO in email and email basically the chief technical officer, hey, I forgot my password for our back server that has all of our secrets. Could you tell me what it is? I forgot. I don't want to reset it. And the dude's like, sure, here it is. And then Anonymous stole everything and ruined them in 24 hours. So in that case, the impact was basically severe, as severe as it can get. So this is a more detailed breakdown from the document of the top 10 application security risks. Injection flaws aren't just limited to SQL. They can be operating system injection flaws. It depends on the application there. LDAP injection, of course, you have to have LDAP running as a component of your web architecture. And basically it tricks the interpreter into executing unintended commands or accessing unauthorized data. Cross-site scripting flaws basically occur when an application takes untrusted data and sends it to the web browser without properly validating and escaping the data. Escaping is basically taking whatever may be a metacharacter and replacing it with something that's safe, so they'll be represented by the same character in the next component, and thus won't be, but not interpreted as a metacharacter, say like the end of a string or start of a command or whatnot. So basically number 3 relates to improperly implemented authentication and session management functionality. Basically it comes down to the web application developer not knowing how to program a login page and how to handle cookies. It's so common that it's the 3rd most exploited thing on the internet. And then the rest, kind of self-explanatory. I don't want to read over all of it because I don't have time. So SQL injection, basically, it's very easy to exploit. It's very commonly exploited. It's moderately easy to detect, and it often has a very severe impact. The business impacts, I would have put severe there too, because if, say, an attacker can get access to your credit card or financial transaction database, they can steal all of your customers' data, and if your customers find out about that, they might not want to do business with you again. So here's a very basic layout for what would happen if I were to, say, go to a website and browse for a new processor because my cat broke my computer. Essentially, in my web browser, I would navigate to basically some online store and go to a page and search for a term called processors. Now, this happens to be using a GET request, so when I send this over the wire, my outgoing application data renders with this GET request category equals processors. And so on the logic layer, it uses that variable and value pair to fill in a pre-coded SQL select statement to get information from this database about products where the category happens to be processors. And so the database will process that, search for all matches, and then compose the results and send them back. So I'll get processors, perhaps, you know, the i7, i5, i4, maybe AMD or ARM processors. And then at the logic tier, basically this gets rendered into a PHP page. All the appropriate pictures and links are constructed for investigating each product more and expanding, perhaps to show more details or customer reviews. And that's all sent back to the user's browser, and you get web pages that get constructed to look like this. So the basics of a database server is that each database server usually hosts many databases. Database servers have users. Some are admins. And information stored about users is stored inside the database. Database users can have permissions set on what they can and cannot do. For instance, user Bob can only access database X, Y, and Z, but not A, B, C. And then there's also other permissions that most people graduate college not knowing about that exist in database that allow you to access the file system from inside the database server. So I can theoretically connect to the database server on another server and then access the file system on that server. There's also other permissions that permit or deny altering, inserting, updating, deleting, or selecting all database tables or specified databases. So the basics to structured query language, SQL, basically you retrieve information from the database using a statement called select. You update information using a statement called update. You add new information, specifically add new records using the insert statement, and you delete information using the delete statement. It's rather straightforward. There's also comments in the language are initiated by minus minus. Anything that follows that in a SQL statement is not interpreted and is considered a comment. So if an attacker were able to inject those metacharacters into your SQL statement, it would comment out the rest of your logic that perhaps restricts some of the results that the user is allowed to see. So information stored in SQL databases are organized in tables. Each row is referred to as a record. So for a user record, you perhaps have the username, first name, last name, address, etc. And each one of these values is defined in a column. So the columns define the data types for each piece of data in each record. So the username is perhaps a varchar 80. Basically it means a string of 8, not 80, but 8, which means a string of 8 characters. Or first name perhaps is a varchar 80, which would be a string of 80 characters. Then there's text, which is basically unrestricted, up to perhaps a predefined constant in the database. And then you'd perhaps have an int for user ID. Now these things can have all sorts of features that allow for specialized joining, for optimization and searching, and make things perform better in searches. But we don't care about any of that. We just care about breaking things. We'll let you guys, if you really want to know that, you can take a database class and learn all about optimization. So results retrieved from queries, say select queries, are also returned in the form of tables. Say you have this table with columns A, B, C, D, and E, and if you just select column A and B, you'll get a table as follows. It's rather straightforward. Which brings us to the next most important thing, the union statement. It allows you to essentially combine the results from 2 select statements. There's some caveats to get it to work. Both select statements have to have an equal number of columns. Usually, they also must have similar data types. And they usually also must have the columns listed in the same order. Some side notes is that by default, union will just return distinct results only. So if you want to get duplicate values, you have to type union all in the place of union. So this brings us to union select and how it's used for SQL injection. So say you have a SQL statement, and we know that if you want to union one SQL statement with another, they have to have the same number of columns. But in the original SQL statement, you have no idea what it is. You perhaps see it on some website, some web page that you know is vulnerable, and you're able to insert a SQL statement into it. In other words, it has SQL injection vulnerability. By using union select, you can iteratively discover how many columns the original SQL statement is selecting. Because if you try to select in your second union a unequal number of columns, it will throw an error. It will typically say, error, union between 2 tables that do not have the same number of columns. So if you try to do select 1, by the way, I'm doing select 1, 2, 3 here. I am not saying from anything. If you type into like a SQL server select 1 or select 2, it's going to return 1 or 2. This is just basically a dummy statement. It's a completely useless statement, but for an attacker, it can be a very useful information gatherer. So If I do union select 1, I'm just selecting a dummy, I'm creating a dummy column, a dummy table with one record in it, and the first column is 1. And if I do select 1, 2, he has 2 columns in there, and it's 1 record and it's 1, 2, respectively, and so on and so on. And I can iteratively do this until I discover, say, there's 5 columns that are being selected in the first table. If I do union select 1, 2, 3, 4, 5, I will get back a valid result, and the web page will usually render properly instead of spewing back an error. So I'll show you guys this later in my demo. Now, it's very common for the original SQL statement to have a huge number of results, and perhaps they get parsed over like 20 pages or so. You only see like 30 results per page. So say we have this statement and it has 90,000 results. And we don't want to have to scroll to the very end to see the results of our attack. You can limit the results via the limit command. Essentially, if we can't handle over 9,000 results, we would just do limit 9,000, or limit x, where x is some integer. So for SQL injection, you could just do limit 0, union select, and then whatever your attack is. That will get rid of all the data from the first SQL statement. It will basically get rid of all the records. It will discard all of the records from the first statement before the union, and then what happens after that is all the results from your SQL injection attack. There's another way to discover how many columns are being selected in the original SQL statement, and that is using order by. It's kind of straightforward. So another thing is that SQL databases can allow file system access. Select load in file is used to read a file, and select into out file or dump file is used to write a file. In advanced SQL injection attacks, the latter command, select into out file, can be used to pass along essentially web shellcode that will be written to a file on the server that you can then access because you just uploaded a web shell, and then you get basically shell command capabilities on that server. So I may show you guys that later in a later lecture. So let's dive into the basics of SQL injection. So there's 3 types of SQL injection. Academically, they're referred to in-band, out-of-band, and inferential. It really comes down to error-based, union-based, and blind. The attack methodology for SQL injection is first you have to identify the injection. Second, you have to identify if your SQL injection vulnerability that you're looking at is dealing with a variable that's either a string or an integer, because those will throw in your way subtle nuances that have to be addressed. Then when you're attacking, you have to decide whether or not you want to use error-based SQL injection, which is the easiest to do. You just simply have to cause an error. But it doesn't necessarily tell you that much. It just tells you there's a SQL injection vulnerability there, and nothing else usually. Then there's union-based SQL injection, where as I showed you, in theory can be used for discovering what the original SQL statement looks like. And there's blind SQL injection. And that's often the case where the web application developer has locked down their application, so they're aware of SQL injection vulnerabilities, so they make sure to not display any SQL server errors. You have a SQL error in the statement at line blah blah blah. You won't get any errors passed from the database server along to the user. They'll all be caught by the web server. So that won't allow any attacker to do number 1, error-based SQL injection. And also, there's often blind SQL injection is the only route when the database is very well locked down. There's good security. There's permissions set that are proper. And so blind SQL injection is an interesting category that I hope we can cover later. Maybe we'll have a project on it later in the class. But most tools out there either do error or blind or a combination. Most tools do not do union-based SQL injection. And that's interesting because union-based SQL injection is where the money's at. Union-based SQL injection is where you get the most data from a database. So let's dive into union-based SQL injection. Say we have this PHP code on the left that handles basically the login page for a website. So you have basically in PHP you establish a SQL Server connection with some hard-coded or included values for the server IP, the username and password to log in the server. Then you have your query constructed, and you're gathering all this data from basically the user's post request, where they include their username and password after hitting login. And then once that's constructed, basically you run the query here, and then the rest of this is essentially for handling the results of that query. In this simple case, it basically checks if the information provided by the user matches a record in the table users where the name equals the user's name and the password equals the password provided by the user. If that result returns in a positive number of rows, in other words, if that result is non-zero, basically it allows that person to be admin. Otherwise, it basically provides an error message, invalid username or password. Now this has no input validation. So in this instance, if I were to enter in Owen and kittens, the SQL statement would then be populated to be where name equals quote Owen, end quote, and password equals quote kittens, end quote. However, if I had to do this, in essence, I enter in whatever data I want, and then I end the string here that is provided in the already constructed SQL statement on the PHP page. To end that, then I can begin other commands. For instance, if I type or 1 equals begin quote 1 and then leave the end quote off because the original statement will provide that, I can basically ask the database, select ID and name from users where the name equals this guy and the password equals this or this. So by that I mean, and the Boolean evaluation here is true or the Boolean evaluation here is true. Now clearly this is always going to be true, so it'll bypass whatever password is set in that database. So this would log me in as admin. So I have a demo. I have a lot of slides on how to do it yourself, so you can go home and do it. This is something I've done a number of times. I did this earlier in the semester, and I've also done it in other workshops for Null Pointer. So I'm going to take you through the process of basically, whoops. So I have this virtual machine, and it's asleep right now, and it's just running a Debian server. There's no GUI because it's not for desktop. And so what I have is the first thing you want to do is once you start up the target virtual machine is you want to discover basically the IP address that it's running as. So you ifconfig and it'll tell you here. So this happens to be running at 192.168.43.130. So what I'm going to show you guys is two things, SQL injection and also using a HTTP proxy. So my proxy of choice, until I discover one that's not based off Java that I like, is Burp Suite. From Burp Suite is made by the guys at portswigger.net, I think. I have the URL in my slides. And essentially, what I have is I have the IP address. Can everyone see that in the back? Is the resolution okay? Raise your hand if you can't see it well. Can you guys move up if you want to see it? Okay. I mean, if you've already seen this before, you know what I'm going to do. So I have this website, and right now I have my HTTP proxy doing nothing. So I can browse this website, and I see that basically there's some title, and it's telling me it's a photo blog. And I'll browse the links, and various pictures come up. And then there's apparently a page that displays all the pictures. It's called all. And then there's an admin login portal. So before we go into SQL injection, I'm going to turn on my intercept. And in my settings, so you guys can see, I have it running at port 8080. So what I've done in Firefox is where did I set this up? Network. So in the advanced settings in Firefox under the network tab, under my connection settings, I've manually configured the proxy to point to localhost running on port 8080. It's really that simple. So any traffic for any HTTP traffic this browser sends out will be first directed to localhost at port 8080. Now, if I don't have my proxy running, it's basically going to say I can't connect to the internet. So I have my proxy running, and right now I have it set to intercept when I turn it on any client requests, so any outbound traffic to servers that match my target scope. That's a good general rule to have. And also I want to look at anything the server sends back to show you guys what's going on when you browse the web. So I also have it intercepting server responses that are in my target scope. So there's a number of tabs in Burp Suite. Target, if you start browsing the internet and you have it running through your proxy and you have your intercept turned off, any site, any URL you browse through, even URLs that are accessed by a site you use to bring in advertisements and third-party data from other domains, they'll get populated in this list. So you can specifically put a scope on, put that in your scope and analyze what's going on with this third party. What is being sent here? So what I've said is basically I have added this IP address to my scope, and I just want to intercept what's going on here. So I'm going to turn on my intercept, and I'm going to go to this page, and it generates a GET request. Make it bigger. I cannot make it bigger. So you see that the first thing in the application request is GET, and then the resource, which is cat.php, and this link is passing along the variable value pair ID equals 1. And then the domain is this IP address, and it's telling the web server all this information about me. So it's telling the web server my web browser information and version, and my operating system version as well. And it tells it what type of data it will accept, what languages it will accept, what encoding it will accept. This is simply for proxy, and as you can see, I don't think I'm even logged in. I cleared everything beforehand, but it's also sending the cookie along with the request. Since HTTP is stateless, it has to do this. So I will forward this along to the web server. The web server processes this, and then it constructs this, and this is the HTTP response from the server. You have HTTP 200. That's the code for OK. You have the date of the response. The server is running Apache 2.2.16. It's also running PHP version 5.3.3. You can configure this to not be provided by the web server usually. And then this is the encoding type allowed by the server. So we'll cover HTML coding in a few slides. Actually, I think, yeah, this is a good point to bring that up. So there's two encoding types that you guys need to know about. The first one is HTML, or also commonly referred to as URL encoding. It essentially converts characters into a format that can be transmitted over the internet, and is generally restricted to the ASCII character set. Any unsafe ASCII characters are replaced by essentially their hexadecimal representation, which in URL encoding is %XX, where XX are the hexadecimal digits. So spaces are commonly replaced with %20 or sometimes by a plus sign. And you can read more about HTML encoding at this URL. So as we saw in that HTTP response, essentially the content type encoding specified by the server is that this is using HTML encoding. The other important one to know about is Unicode. Unicode is essentially aims to be a universal character set. It aims to be a superset of all other character sets for all languages, for all alphabets in the world. So there's three main types of Unicode: UTF-8, UTF-16, and UTF-32. I've listed the specifics for each one as to how many bytes are used for their specific cases. UTF-8 is very, very common. So the last thing I want to cover about encoding is that you all should be familiar with basically character escapes. So here %20 is a space, %41 should be capital A, and et cetera, et cetera. So this could be very useful for an attacker when bypassing perhaps intrusion detection filters or web application firewall filters. Say the web application firewall, which we'll cover later, essentially sits in front of the web application and filters all the data going to it. Make sure there's no bad data going to it. So for instance, maybe it's filtering out everything that looks like union, select, and SQL injection. So it's filtering out all the union-based SQL injection. But it's just looking for basically UNION. If you represent it all in hexadecimal with Unicode encoding or HTML encoding, it can almost always, it should bypass that filter. In other words, the filter will be like, okay, this doesn't look like malicious data. All right, so back to this. So that covers roughly encoding and HTTP intercepts. So this brings us to essentially discovering SQL injection vulnerabilities now. Since the data is being passed along to the web server in GET requests, the value and the variable and value pairs are being stored here in the URL. So I can just manipulate them here. If they weren't, say in the case it was post, all that variable value pair data that the application needs will be sent in the application request. It wouldn't be in essentially the URL here. So you would need to intercept it in order to tamper with it. But in this case, you don't have to. So what I can do is I can do my SQL injection discovery simply just by manipulating the URL in the browser. The most common way to discover whether or not something has a SQL injection vulnerability is to try and cause an error. Now, if I insert something that perhaps throws off the string parsing, like inserting an extra tick or double quote, or perhaps there's no ticks or double quotes in the original statement, when it gets passed along to the database server, it will see either an odd number of quotes or a quote standing all by itself, and it won't know what to do. So essentially respond with, why did it do this? Replace the line. There we go. That was just Firefox. I don't know why that's happening. So, let's blow this up. So this is an example of a SQL Server error. You have an error in your SQL syntax. Check the manual, blah, 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 blah. Basically a very uninformative statement for someone who's getting started with SQL. So this tells me that this page has a SQL injection vulnerability because I can cause the database to encounter an error. So we don't know, we want to use this to extract data now, but we don't know what the original SQL statement behind this is. We see that there's probably two things at the very least it's selecting. There's some probably title here, and then there's a URL or a file name to display the image that corresponds to it. So what we're going to do is we're going to do union select 1, 2, because we know there's at least 2. And now we get a SQL error in the reply saying that the select statements have a different number of columns. So let's try 3. And still error. And so let's try 4. And what has happened is that the combination of these two SQL statements has succeeded because the column numbers are equal. Now, this is a one record table with equal number of columns that's simply populated with 1, 2, 3, 4. So we know that by putting 2 here, that something is happening with the logic to display the second value in the record here. So this would be a good spot to start extracting data. So we've identified essentially the underlying structure of this vulnerable SQL statement, and we've also identified one of the best places to replace our SQL injection with something that can actually begin to extract data. So these are all slides, so you guys can do it at home. Depending on the server, there are some very basic variables that are commonly targeted to find out more information about the database. Usually there's basic functions that you can call, like database parentheses, user parentheses, at version, or sometimes version parentheses, and data dir. So I'm going to go through each one of these and show you essentially. So database parentheses. So the database is titled photo blog. That's not surprising. Let's see user. This will tell us the user that the PHP pages are using to interact with the database. So the username for the SQL server is Pentester Lab at localhost. So the version, which we also found out, well, no, I misspoke. So the version for the PHP is the version of the database server happens to be 5.1.63, and it's, I guess, squeeze 1. So with that information alone, say the system was completely locked down, I couldn't extract any more information off that. What I could do at that point is I could, with the information that I've intercepted, from the server that is running Apache 2.2.16, it's running PHP 5.3.3, and it's running the SQL Server version of Squeeze 1 that has version 5.1.63-0. I could set up my own system with all of these exact things and start fuzzing it and doing vulnerability discovery on this if I were so inclined. Say I'm a bad guy and I want to steal millions of dollars. It's completely plausible to go about basically setting up your own environment similar to your target and finding all the vulnerabilities that you can in it. So I'm going to turn off my intercept. And so we've got the version. Another thing that's useful to know if you're doing any file system access is the data dir. So the database happens to be running out of the directory var lib mysql. So these are all just general variables so you can query without referencing select from another table. So let's get on to select from another table. The most interesting target usually, unless it's locked down by the database administrator, is the information schema table that's present in every database. The information schema table contains all the information about how the database is laid out, who the users are, what they can do, as well as for each table, what each column is and what it contains, and other information. So we want to do select that's right. I have this written down for reference. Information schema, table underscore name. This should not work. It doesn't exist. It's what columns. I tested this earlier and it worked fine. Funny. Is my intercept on? That would be doing it. No, intercept is off. No. Wah wah. Anyone see with a sharp eye what I'm doing wrong? Maybe I've missed. Ah, here we go. Just missing half. Okay. Success. Sorry, that was a typo. So what we have is a very large list of data of all the table names from the information schema. So there's a table called character sets, whatever this is, columns, column privileges, engines, events, etc., plugins, schemata, session status, statistics. There's a table called tables, table privileges, views, user privileges, lastly, users. So there's the admin console for this photo blog, and the information for that console is likely stored in this database. So we want to know essentially what column names are in there. So we can do that by basically selecting instead of table name, column names. And here we get every single column for every single table, and it's a lot of information to sort through. But we notice at the end, so essentially in the users table, there's a thing with columns for login and password. So with this vulnerability, we can search for password from, instead of the information schema.columns table, we want to search for it from users. And what we get is an MD5 hash. So I believe many versions of SQL Server store, well, that's wrong, because it happens in the logic layer. Many beginning application developers just simply MD5 hash their passwords for being stored in the database. If you maybe get hired by some crappy business like you probably would just end up storing your passwords and all your information in completely clear text, so that when you get broken in, you have to basically send out a huge apology to all your users that all your passwords have been stolen along with all your credit card information, because we don't encrypt anything, we have no permissions, and by the way, you should probably get identity theft insurance. Good game. So what we can do is, so we have this MD5 hash, and say we have no idea what we're doing with it. We can just basically Google search for an MD5 cracker website, and I just copy and paste it in and fill out this CAPTCHA. And it tells me that in literally milliseconds that the password that this is cracked to is password. So, and clearly this is just an academic example. So I'm going to go to the admin. Well, I'm going to go back because I don't know what actually the username for the admin account is. So I'm going to go see what the login is, and it's admin. Could have guessed it, but so we just type admin, and then we copy and paste basically what we got, and boom, we get into the admin console. So here we can begin defacing a website if we'd like. But we want to explore what we're allowed to do here. So we see that it seems like there's some sort of option to delete resources, but I think this corresponds to either users or pictures. So let's go to Manage Pictures. It seems to be the same page. Let's go to New Picture. Now this is interesting. It's asking us to browse for a file. So it looks like we can upload a picture. So at this point, we have access to the content management system or the admin console, and we can upload files onto the server. A common thing to upload would be something that allows us to do more to the web server, something that, for instance, allows shell command access. So what I have is a nice little short PHP file that essentially from get has a variable cmd, and whatever its value is, it runs it in system. All this other stuff you don't have to worry about. It's just a little piece of garbage to defeat some nuance bug in I think the web server for this. So what I'm going to do is I'm going to browse to that. And I'm going to call it backdoor. And I'm going to upload it. Now I get this error message back that says no PHP. So there's some sort of security filter to prevent users from uploading code that can be run on the web server, for instance, PHP. Now, what web application developers commonly do is they don't know about all the old legacy versions of file types that are still validly interpreted by language interpreters like PHP. So .php is the most common file extension for PHP files. However, there's an old one called .php3. Clearly that's for PHP version 3 and whatever. But what I can do is I can save this as .php and hopefully Windows doesn't screw up the file extension, and try again. So I'll try this old thing that perhaps the web application developer didn't think of. And we'll add it. Now, it has worked, and it's told me that basically this is a SQL statement behind it, because this is a very rough admin console. Essentially, it is named it somewhere webshell.php 3 on the file server. Now, if I just type here, I probably won't get it because it's storing it somewhere else. So what I need to do is find the place that's storing all the images. The easiest way to do that is simply just to inspect the element to find out where on the web server it's being stored. So this is really tiny. So it's storing in admin/upload/ there. So what I do is I do uploads that, and it seems to work. And what I do is do cmd equals, say for instance, ls. And it's telling me the results of ls in that directory. So some important things to note about web shell, or web shells in general, is that very basic ones, every command you execute is in its own context. It's completely independent of the previous command. So I can't do cd ... enter, cd ... enter, and then so on and so on. It's going to be in the same directory every single time. Same context every single time, independent of everything you've done previously, unless you've actually changed something on the file system, like remove files and whatnot. So what I can do is, since the etc password file is usually world readable, is I can do cat/etc password here. And this gives me a very rough look at the etc password file. Now clearly the passwords are not stored in here for root. They're marked by X, which indicates they're actually stored in the shadow file. So shadow should not be readable by this account, and thus I get a blank result, meaning basically permission denied, so no data is returned. But in essence, I have a working web shell, and I can move on and establish more access from there. But I have to move on because I need to get through the lecture in about 10 minutes. So moving on to cross-site scripting as fast as we can. So other related injection vectors include LDAP, XPath, XML, XSLT. I don't even know what that is. So this is a wonderful resource for defending against SQL injection attacks in almost every common language for web applications, PHP, whatever, ASP, you know. So the basic defenses come down to using parameterized queries, but this is not always an option, and then using stored procedures. So you don't dynamically build SQL statements, but that's also very limiting as well. And then it also comes down to proper encoding. And you can read more about that at this site. It's pretty easy to read. So if you're doing SQL injection attack, these are wonderful resources, basically cheat sheets. The second one is a kind of interactive little cheat sheet that shows you common filters and how to bypass them. For instance, in my previous SQL injection, let's just go back as far as we can if it'll let us. So, for instance, for this, what you can do is there's various ways to get around the filtering of things like union. You can insert start and end comments in PHP, and this sometimes will work, but that's just a bad example that happens to not work there. So let's get to cross-site scripting, the top two, the second most important vulnerability. Essentially, it is moderately difficult to exploit. It's extremely widespread. It's also very easy to detect, and it can have a moderate impact. So let's go over some browser notes first. Very important thing to know about is same origin policy. This is a very important policy that's implemented in most, well, nowadays implemented in all modern browsers. It essentially restricts how a document or script loaded from one origin can interact with resources from another origin. It is meant primarily to prevent cross-site issues. So for instance, evil.com cannot access content from bank.com because this is a different domain. So same origin policy is implemented everywhere, not just in web browsers. And because of that, it gets implemented differently. So there may be little nuances in the Internet Explorer that are different than Chrome, for instance. So the permissions require the following matches for something to allow access for a resource to be read. The ports on both of the two domains have to match. The domains both have to be the same, and the subdomains commonly have to be the same. So this is taken from Wikipedia, of basic combinations of things that will result in failure, and success. So there are exceptions to this. I said that the subdomains have to be the same, but it's also common for two different subdomains under the same domain to be allowed to share content between the two. And a really good academic example would be content between secure.live.com and vulnerable.live.com can be shared. Now clearly you can see that there could be just problems there. So there's also wildcards that are allowed, like star.google.com and star.whatever.com. So the risk here is basically is domain lowering. You're perhaps lowering the standards required for a certain domain or subdomain by allowing scripts or documents to interact with perhaps lower standard domains, or rather subdomains. So what this means for scripts is that when exposing or including a resource across a domain, such as JSON or JavaScript, is that basically when documents do not have the same origin, specifically in JavaScript, the access is simply limited to other resources to the window and location objects. Some browsers, perhaps even mobile browsers, allow even more access though. There are common functions in the JavaScript API that allow documents to directly reference each other. And so by documents, I mean web pages. So iframe, window.parent, window.open, and window.opener. Same origin policy and cookies. Cookies, by default, allow read and write access if the domain is the same, and that's it. So vulnerable.live.com and secure.live.com can share cookies. So there's no check on port numbers, and there's no check on any schemes, whether maybe there's a secure setting in the cookie or it's HTTP only, perhaps, because well, HTTP only will prevent JavaScript from writing to it in the first place, but that's a specific case. So cross-site scripting is a very serious problem. It's probably been a serious problem since the beginning of time. It's not language specific, and all web applications, all web platforms are vulnerable. There are multiple variations, and we'll only be able to get through stored cross-site scripting today. There's no real easy fix, and they're very well known. See OWASP for more details there. So SQL injection clearly targets the database server. Cross-site scripting can target a number of things. However, it usually just targets other users. So cross-site scripting is essentially script injection. OWASP number 1 is simply labeled as injection. So this is script injection that is executed on the client side, not necessarily like injection flaws, which are typically just executed on the server side. So the goals for the attackers here are basically to get the web server to distribute malicious scripts to other users to be executed on the client side. So here's this really simple example. Say we have just a forum where people post questions and comments and answers. And so you have forums all over the internet for like Linux help, for gaming, for fantasy football. And so users can post comments and posts. So say we have fantasyquidditchleague.com, basically, and someone basically posts their whatever on the forum. And so these comments are in the form of text. And if they're not secured at all, an attacker can post comments as well. These comments can have a script in them. And this allows for cross-site scripting attacks. It will simply just be when it's sent to the server, his cross-site scripting attack will simply just be stored in the database, and whenever someone visits that page or a page with that comment, typically just that forum thread, the database will populate all the comments, populate the page with all the comments for that thread, and that script will then be put into the HTML content for that page, and whenever anyone visits it, their browser will execute that JavaScript, and thus they'll be attacked by the cross-site scripting. So that also requires that they have JavaScript enabled. So the second example is, imagine some classified ad website. Let's just go with bladeslist.com. So users can post very simple ads, blah, 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 secure web developer needed, and they send this off to the web server. Now, this gets basically inserted into a database, and then when users basically view the available ads, each ad basically gets rendered into an HTML page. So typically you have static content, and at some point what's inserted into it is the contents of each ad. Say a user clicks on a specific ad, it takes them to this web page, and this web page is basically following some template where you have this static code, HTML, body, etc., and then this dynamic content is being pulled from the database where it's being stored. So users who view that get to see it, and it's all rendered in HTML, and this is fine, it works, but it's not secure because it's not filtered. So I can, since it's being just rendered as straight HTML here, I can insert HTML code, and a common thing attackers do is basically script the tag, HTML tag for starting and ending a script. And I just have comments here for blah, blah, ooh, evil JavaScript. And this gets rendered in with the static content. So essentially, whenever a user views that ad or sees that ad, and that content gets put into the HTML, that script will run. And usually, there will be no visual indication that a cross-site scripting attack is running in the background for a user. The victims will be 100% clueless. Like, it takes zero time and leaves no indication. So what can attackers do with XSS? The most common attack is really to steal session ID, and in JavaScript that's referred to by document.cookie. Another thing is to deface websites, and related to that is clickjacking. So basically defacing a website, you could put a JavaScript layer in front of whatever the page is with all sorts of whatever you want, graffiti and whatnot. So for clickjacking, you have basically a transparent layer in front that the user thinks is legit, but it's actually storing all of the username and password information. So can we defend against this by just blocking the script HTML tag to be safe? The answer is no. You can still do cross-site scripting without simply the script tag. So the third example here is basically, say you have a social media website and you have this form to sign up. So there's first name, last name, etc. And essentially the code that handles this is basically input, the type here that's expecting is text, the ID is fname, and the value is this. So when I type in Bob, Bob gets populated in here in the value, okay? So consider this input. An attacker can construct a valid attribute that triggers JavaScript for any input type. So say this gets rendered the value Bob, the user's name, gets rendered on a website, say on a button, like click to add friends with Bob, or click to become friends with Bob, or send Bob a message. If I were to insert this, whenever someone mouse over that element, it would trigger this JavaScript. Now I'd have to populate what evil is in here to do something, but essentially this would become here, and this gets stored in the database. And when that gets rendered on the HTML page, the user sees this, and the attribute that's being rendered there has this on mouse over event tagged to it, and it will spawn that JavaScript handler, event handler for any mouse overs on that element. And so anyone who mouse over that text box will be hit by the XSS attack, and they'll be completely clueless as to what just happened. There'll be no indication. So this, hopefully I'm not too over time, is basically a real example of cross-site scripting code that can steal session IDs. Essentially, for instance, instead of on mouse over, on click this element, essentially what I do is I trigger this, I point it to the following JavaScript that is essentially, I'm sending to basically a domain I control that's running a thing that I've set up called xss.php. The value, the variable and value for C equals, and what I do is I have here escape document.cookie. This JavaScript essentially takes the cookie for your current web page and sends it in a GET request to get a JavaScript from my malicious web page. I don't have to return a JavaScript. I don't have to return any script. I've just logged your cookie, and that's all I need to hijack your session. So anyone who clicks on this will have their cookie sent to my site. And so, for instance, what I can do is I can be a bad guy. I can go on the social media website, set up my page so when they mouse over me or click on my name, it will trigger this action. So what I can do to target an admin is I can misbehave, break the terms of service, so they have to deal with me. Say I just troll and flame nonstop, and the admin's like, okay, we have to ban this guy. So he goes to click on my name, and boom, he sends his cookie off to me, and now I impersonate the admin. So the conclusion is really we've only covered one form of cross-site scripting, and there's others. This is a great cheat sheet for defending against cross-site scripting. Essentially comes down to you must validate and encode. Encoding must be contextual. There's also whitelist validation. I really just refer you to the bug cheat sheet. This is for attacking with cross-site scripting. Any questions? That was a lot, yes.
How do you go about detecting it? Because I know in SQL you have to do ways of detecting it quite easily for cross-site scripting.
I'm not aware of all the common ways to detect cross-site scripting. In theory, you could have on the server side an emulator that basically any content that's about to be sent out to a user, you emulate it on the server side every now and then. But clearly that will take some time, especially with resource-intense websites. Yeah.
How can you get the password from the hash so quickly?
So commonly what you're doing when you're cracking hashes is there's a number of tools you can use. You can use dictionaries, and basically if the hash has salt, essentially you append the salt to everything in the dictionary and you hash it, and you look for a matching hash. Or in the case of something that's not collision resistant, you can brute force it, try all possible combinations, and you'll basically through the birthday paradox get lucky and find a matching collision. In this case, password P4SHWRD having you found before the other matching collision. And it's also common password.
Yeah, common. So then you just use the tool.
So yeah, I think we'll cover rainbow tables later on. It's a very efficient technique for tracking.
Okay, you just paste.
I just pasted it into some other service that's being hosted by some other people to do this.
Okay, you just paste.